this chapter, we will be looking at various types of functions. In this lesson, we will be looking at the relationship between polynomial equations and their graphs.
Okay, so we started last time starting to develop an idea here, or a link between some vocabulary here, and we're going to carry on with this. So again, just to reiterate here, let's say we're considering the function f of x is equal to x squared plus 2x minus 15. Okay, we'll zoom in a little bit. Okay, when we factor this guy down here, we're going to get x plus 5 and x minus 3. Okay, now the zeros of the function, and that'll occur when we make the y value, the value of the function, equal to 0. So whatever value of x makes that true, makes this whole expression equal to 0, we call those the zeros of the function. In this case, it's negative 5 and 3. If you plug negative 5 into this factor, we get a 0. Doesn't matter what it's multiplied by, it's going to make it equal to 0. Same thing if you plug 3 into this factor, it's going to make this equal to 0. And again, doesn't matter what you multiply it by, the result will be 0. Okay, so that's what we call a zero of the function. Those correspond to the x-intercepts of the graph, and you can see that fairly clearly here because we're replacing the y-coordinate with a 0, okay, and asking what value of x makes that true. Well, graphically, where the y-coordinate goes to 0, that's the x-intercept of the graph. Additionally, as soon as you plug in a 0 in for this, what you're left with here is an equation, okay? There's now no longer a relationship here that's visible between x and y, y the variable per se. It's this expression here equal to 0, and now we're going to solve that and look for the roots of the equation. Those are all the same things. And we've talked about that before, trying to link those ideas here. Now, we're going to take this one step further, because sometimes when you're building a polynomial, sometimes factors, okay, for example, like in this case here, maybe the x plus 5, okay, or the x minus 3, sometimes these factors show up more than once in the factored expression of that function. The number of times it shows up is called its multiplicity, okay? So if you're to put it, for example, if I was to have something like this, f of x, and I was to build it and make it x plus 5, and it turned out there were 2 of them, so it was squared, and then maybe x minus 3, and let's say there were 3 of those, so I had a cube there. This function right here, this factor I should say, has got a multiplicity of 2. This factor here has got a multiplicity of 3. Now, what we want to do is link the multiplicities to properties of the graph here. Okay, and you can see that right here. So the multiplicity of a 0 or x-intercept corresponds to the number of times a factor is repeated. Now, let's take a quick look at this. If you've got a factor that has a multiplicity of 1, it only shows up once in the factored form, then what happens is the graph simply cuts through the x-axis at that point, just straight through, straight through, straight through. However, if that graph has that factor there has a multiplicity of 2, this is what it looks like. Okay, the graph will come down to it, touch the x-axis, and then bounce back up here. So when it has a multiplicity of 2, think of it like this: it's being squared. Okay, now slightly to the left, slightly to the right. Okay, that function there is going to either be positive or negative, but when you square it, it'll make it positive. Now, this can also come up from below, okay, because it is possible to throw a negative in front of something that's being squared, and the overall result is negative. So a multiplicity of 2, though, think of it like this. It comes up, is tangent to, okay, the graph is tangent to the x-axis. That's what's going on right there. Okay, tangent to the x-axis. Over here, we get a multiplicity of 3, and what a multiplicity of 3 does is it comes up and it looks like it might want to bounce off like it did over here, but instead it kind of levels out and then passes through and keeps going. Okay, we call that a point of inflection, okay, where all of a sudden, and essentially you're getting kind of this change of curvature. It kind of changes, so it's curved down, and then all of a sudden it passes through and curves back up again. But this is what a multiplicity of 3 looks like. Now, we could continue on and look at multiplicities of 4, 5, and so on. However, every even multiplicity is going to roughly look like this. Okay? You increase the multiplicity, and what happens is you increase how steeply the graph approaches the x-axis, but it's basically going to look the same thing, like the same thing here. A multiplicity of 5 and 7 is going to look roughly like this. It's going to get a little steeper, come in a little bit more dramatically, and then leave a little bit quicker. But it's still going to have basically this shape here. So the maximum we're going to look at here will be multiplicities of 2 and 3, or I should say 1, 2, and 3. But we're not going to go beyond that. And actually we know, based on the curriculum here, that we're not going to look at polynomials with a degree larger than 5 anyway on the major exams here. So you can see how you maybe put together a graph that's got a root of a multiplicity of 2 and a multiplicity of 3, and that kind of covers it. But anyway, so the main idea right now is that we want to have a link between factoring, okay, factoring an expression to get its x-intercepts, okay, but being able to do more than that. Now that we know the x-intercepts, by looking at the factored form, we can determine how that graph interacts with the x-axis. It's either cutting straight through, it's tangent to the x-axis, or has this little inflection point on the x-axis.
Use the polynomial function below to determine the multiplicity of each factor. What would happen to the graph at each x-intercept?
Okay, so really in essence, this question's kind of been answered for us here. We've got this x plus 3, x plus 3, x minus 4, x minus 4. So this factor here shows up twice, it's got a multiplicity of 2. This factor here shows up twice, it's got a multiplicity of 2. Now, we're supposed to, at this point here, identify what's going to happen with each x-intercept here. Well, what we've got here are going to be a couple of tangents, okay? Now, let's think about what this graph might look like. We'll just have a guess here. My x-intercepts here, okay, my x-intercepts are going to be negative 3 and positive 4. Okay, so on the graph, I know that this graph is going to hit at negative 3. It's going to hit over here at positive 4. Now, I can make some other claims about this thing. Now, notice I've got x plus 3 has got a multiplicity of 2, x minus 4 has got a multiplicity of 2. That means together, like, let's just look at it like this. This is quadratic. If you expanded this out, you get a quadratic. If you expanded this out, you get a quadratic. A quadratic multiplied by a quadratic is going to be a 4th degree function, okay? So if you take the multiplicities of those roots and add them, you're going to get the degree of the function. So the sum of the multiplicities equals the degree of the function. So I know this is going to be a 4th degree function, okay? I know as well that I'm going to get positive x squared here, because these things, if they're being squared, okay, even if there was a negative in front there, inside the parentheses, I would still get a positive when I squared it. Positive times a positive is a positive. So what we've got here is a positive quartic. Now we've already had a kind of a look at what that means here. That means we've got this kind of a bowl shape here. It's going to, sorry, not bowl shape, but it's going to open up. Okay, it's going to be like a W shape here. I also know that it's going to come down and it's going to be tangent to those two roots here. Positive because it's, okay, sorry, opens up because it's positive. It's going to change directions once, twice, 3 times because it's a quartic. And again, it's going to continue back up because it's a positive quartic here. So it's going to start in quadrant 2, end in quadrant 1. It's got to look something like this. Now I could do a little bit more with this, but the question was basically how does it intersect with the x-axis here, and that's what we're looking for. If we really wanted to, we could do a little bit more just to give ourselves a bit of a sense of how far up it goes here. I could determine the y-intercept by simply making x equal to 0, okay, and that's going to give me 3 squared, or 9 times 16. So I know this would go up here at 144. Okay, if I need a little bit more detail than that. My scale then is quite out of whack here, but anyway, that's what we are expecting this graph to look like, sort of.
Identify the specified properties of the following graphs.
All right, so let's take a look and see what information we can pull out of this. So notice it's changing directions twice here, which suggests to me that this is a cubic, a degree 3. Okay, because I would expect the degree to be 1 more than the number of turning points that I've got here. Now, that's not always true. That this could be a higher degree. We kind of have to make the assumption that what we're looking at here is all there is in terms of activity on the graph here. Okay, so I'm assuming degree 3. My x-intercepts here are going to be negative 4 and looks like positive 1. Now that means, sorry, write that a little darker there. Negative 4 and positive 1. That means that I'm going to have factors here. If the x-intercept is negative 4, one of my factors is going to be x plus 4. And if my other factor, sorry, my x-intercept is 1, one of my other factors is going to be x minus 1. Now that's only two factors there, and I've got a degree 3, so there must be something about their multiplicities. Notice that the graph just cuts right through at negative 4. So this has got a multiplicity of 1. But at negative 1, at positive 1, the graph comes up and it's just tangent to the x-axis there. So this has got a multiplicity of 2. Now, there's my degree of 3, the sum of the multiplicities. Okay? I know that this starts, okay, if you look at the ends, okay, at the far ends here, this thing is going from quadrant 2 to quadrant 4, which indicates a negative leading coefficient. Okay, the graph is dropping down. Now it turns out I can actually do a little bit better than that. I could actually figure this out, and in fact, in a couple minutes here, I will. I'll come up with the actual equation for this thing. Sorry. Now the interval where the function is positive. So this is asking me where the function is greater than 0. Now not or equal to 0, just greater than 0. Now just take a quick look at this. Think of this as like a road, okay, and we've got this border here, okay, dividing, I don't know, could be two different countries, could be like Canada and the US, it could be anything here, but it's like a road here. The question is essentially asking when, like I already know what my x values are. I'm asking for what values of x is the graph above the border, okay, above that line here. Or in other words here, think of it like this. If I'm asking where y is positive, what I'm referring to here are quadrants, okay, quadrants 1 and 2. That's what I'm looking for, quadrants 1 and 2, because this is where y is positive. Y is negative down here, I'm not interested in that. So where is this graph positive? Where is it up here? Well, to answer that question is the same as when I answer almost any question like this, or like solving an equation or whatever. I answer given x. The only thing I can answer with is x. So what values of x make this thing positive? And the answers are wherever x is less than negative 4. Now it's an interesting question to ask, what interval is such that the function is negative? Where is the function negative? Now that's where y is less than 0, and that is quads 3 and 4. So now I'm no longer interested in this. Okay, now notice it's not less than or equal to 0, just less than 0. And again, I can only answer by giving x values, because that's what I have control over. So I'm essentially going to tell you what values of x you plug into the function in order to expect a negative value here. Now, negative 4 is where that starts. Okay, if you go to the left of negative 4, it's nothing. But to the right of negative 4, okay, when x is greater than negative 4, yeah, these are all in quadrant 3 and in quadrant 4. Except for one little thing, right here. Right here, the function doesn't do that. Right there, the function is at 0. Well, 0 is not less than 0. So what we have to do here is we have to state, but don't include 1 in there. So we're going to use all the values of x where x is greater than negative 4, but don't include the 1. Okay, now I'm going to take you, we're going to go back here and we're going to talk about that sign of the leading coefficient again. Sorry, I'm just looking for, and I don't have it. That is okay. I apologize if the pink post-it is a little too bright. Okay? Here's what we're going to do here. I know right now that my function would look like this. It's going to have some sort of, oh, you can't see that hardly at all here. I tell you what, I will make this better to see. I'll use this. Y is equal to a, and I know my two roots here were going to be, what is it, x plus 4 to the 1, x minus 1 squared. Now, sorry, I'll move this over and have a quick look at this. Look at my graph here. What I need is one other point to help me out here. Now, I don't know that this was specifically intended, but it really does look like the point 0, negative 4 is on that graph. So with one extra point here, I think I can come up with that stretch factor, the leading coefficient, if you will. That occurs, okay, because I've got the point 0, negative 4 in my graph here. Negative 4 will equal a, 0 plus 4, 0 minus 1 squared. Well, negative 4 is going to equal, okay, well 0 plus 4 is just going to be 4. 0 minus 1 is negative 1, but squared is going to be positive 1. So this is just going to be a times 4. And now I can divide, and I'll get a is equal to negative 1. Now, I knew a was going to be negative, okay? I anticipated that. But now I can see that for sure here. So therefore, my equation here will be negative x plus 4 times x minus 1 squared. I could expand that out, but that's really got all the information that I need right there. I'm happy with that. In fact, I can see the factors quite clearly. So this is me just taking that leading coefficient question there, just taking it one step further. Okay, so let's take a look at this one here. Now, notice this has only got really like 2 spots here that look like it's changing direction here. But this little change of direction here is a little wonky here because it looks like it wanted to come back down, but it kind of went back up here. What you got to do now when you're looking at this is think of it in terms of multiplicities here. This root here has definitely got a multiplicity of 1. This root here, because it's got this little inflection point, it's changing its curvature, kind of this little S thing, this has got a multiplicity of 3. So together, add those up, this has got a degree of 4. That's the degree of this function. And it looks like I would anticipate. It's got this kind of a sort of a warped W shape here, but that's definitely a quartic, a degree 4. My x-intercepts here are going to be negative 4 and looks like positive 3. Now you kind of have to guess at that a little bit, but that's kind of in the middle of the motion there. And that corresponds to factors x plus 4, which I've already indicated has a multiplicity of 1, and then x minus 3, and again, I've indicated that the multiplicity here is a 3. Okay, so that kind of suggests a structure to this polynomial here. We'll talk about that in a second here. So it's an even degree function. I see that it goes from quadrant 2 and goes over here and ends in quadrant 1. So now that suggests to me a positive leading coefficient. Okay, basically the little shape here opens upwards, which suggests positive. Interval where the function is positive. Now remember, what this means is I'm looking for where is this thing in quadrants 1 and 2. Okay, so kind of cancel that out here. Where is it in 1 and 2? Well, that's this piece here, and that's this piece here. Now, but I have to answer using the only thing that I have control over here, which is the x-coordinates. And so that's going to be to the left of negative 4, which means x is less than negative 4, together with to the right of or greater than positive 3. So out those directions here, that's where this graph is going to be positive, where the y values are going to be positive. The next question here says, show me the interval where the function is negative. Well, remember, that means quadrants 3 and 4. So we're looking down here, and again, I answer that using the only thing that I have control over, which is the x-coordinates here, and that's going to be from negative 4. If you slide along here, as soon as I hit negative 4, I'm down negative here, up to 3, and away I go here. So this is going to be between negative 4 and 3, not including, because I didn't ask you where does it actually equal 0. Okay, so now we're going to come up with the equation of this polynomial here really quickly here. We know it's a quadratic. We got 2 factors here. This point right here, I need another point here. This point is probably the best one here. This is the point here, 1 comma negative 4. Okay, and I'm going to utilize that to help me get my function here. So let's take a quick look here. So this is going to be y equals a. I've got the factor x plus 4 with a multiplicity of 1 and x minus 3 with a multiplicity of 3. If I take and plug that point in, 1 negative 4, so this will be negative 4 is equal to a times 1 plus 4 times 1 minus 3 cubed, and evaluate this. Okay, well 1 plus 4, that's 5, that's nothing. 1 minus 3 is going to be negative 2, cubed is negative 8. So 5 times negative 8, negative 40. And if I divide, I'm going to get positive 1/10 is a. So therefore, my equation is 1/10 x plus 4 times x minus 3 cubed. Now that's the best guess. I'm not entirely sure if that was the intended point that's on that graph here, but that's the point that I used here. And it corresponded quite nicely with my prediction there that the leading coefficient was positive.
Determine the equation with minimum degree for each polynomial function. A quintic function with zeros -1 with a multiplicity of 2, 3 with a multiplicity of 1, and -2 with a multiplicity of 2, having a constant term of -12.
Okay, so let's just jump right in here and start listing things off here. We've got a quintic function with zeros, okay, -1. Now that means if we've got a 0 of -1, our factor is going to be x plus 1, and it's got to have a multiplicity of 2. So we know that's going to be squared here. The next one says we've got a factor, or 0 of 3, which means the factor is going to be x minus 3. It's got a multiplicity of 1, so to the 1. And then we've got -2 is a 0, so we're going to have x plus 2, and this also has a multiplicity of 2. So here's going to be our function here, and now we're told that it's going to have a constant term of -12. Now it is very tempting to want to just put a -12 at the end there, but actually that's not true. That's not the way that works, because what happens here is when you expand these guys out, you are going to get a constant. Okay, when you expand this out, okay, you will get a constant. The constant term exists only when these things are all kind of written out, foiled out in a whole bit here. So watch what happens here. My constant terms here, this is going to be 1 squared times -3 times 2 squared. That's going to be my constant here. So 1 squared is just 1. That's not going to do anything. But -3 times +4. Okay, well there's my -12. That is -12. So normally what I would have here is an A of a stretch factor. Okay. But with I'm already convinced that my stretch factor here is going to be 1, because if I'm going to have a constant term, that means my y-intercept is going to be -12. My y-intercept here, -12, is going to occur where x is equal to 1. Sorry, I can't believe I said that, not 1. That one right there, where x is 0. That was weirdness. 0 plus 2 squared here. And when I evaluate this and then divide it through, I'm going to get that a is equal to +1. Which means that my overall function is simply going to be exactly what I had written originally. Okay, that there didn't need to be a stretch factor there to get a constant value of -12 when you expand that out.
A quartic function with zeros 2 with a multiplicity of 3, and -5, and with a y-intercept of 30.
So this one right here, our zeros are 2, so a 0 of 2 means I'm going to have x minus 2. This has got a multiplicity of 3. And then it just says that I've got a 0 of -5, so it's going to have a factor x plus 5 there. Now, the y-intercept is supposed to be 30. Now, the y-intercept would be the constant term. Again, I'm assuming that there's some sort of vertical stretch occurring here. Maybe not. In the previous question, there was no vertical stretch, but there might be in this case. If the y-intercept is 30, that means if I plug a 0 in, okay, if I plug a 0 in for x, the result should be 30. Now let's just take a quick look at this. So 30 should be a times, well, 0 minus 2 is -2, cubed is going to be -8. -8 times 5 is going to be -40. And when I divide that through here, I am going to get that a is equal to -3/4. So if a is -3/4, then my constant term, or my y-intercept for this function, will be 30. So therefore, I can write y equals -3/4, x minus 2 cubed, x plus 5, and that's the equation of my function.
The graphs of two polynomial functions are given below. Determine the equation of each function in factored form.
All right, so we're going to come up with the equation of this particular polynomial here. Now, I can see that it's got an x-intercept here of -3, an x-intercept here of -1, and then an x-intercept here of +2. Now, the multiplicities of those two zeros there are going to each be 1. This has a multiplicity of 2. So I can write out my equation. Okay, and I haven't got a lot of room, so I'm going to do it like this. So my equation is going to look like this. It's going to be, there's going to be a stretch factor there. This will be x plus 3 to the 1 times x plus 1 to the 1. And then this has got a multiplicity of 2, so this will be x minus 2 squared. Okay, good. So there's the form of my my function right here based on the graph that I'm seeing based on the zeros here. Now, I'm also told that it goes through this point right here. It's got a y-intercept of, what is that? The scale's going up by 2, so it's going to be 6. So if the y-intercept is 6, if I plug 6 into y and 0 in for x, okay, 6 is going to equal a times, well, this is going to be 3. 3 times 1 is just 3. And then negative 2 squared is going to be positive 4. So 3 times 4 is going to be 12. And if I divide, I'm going to get that a is equal to 1/2. So as long as this thing has a stretch factor, vertical stretch by a factor of a half, that works to get the function that I'm seeing right there. So therefore, my equation is y equals 1/2 x plus 3, x plus 1, x minus 2 squared. That's the equation of the function. Right there. So once again, to come up with the equation of the function here, we got to identify the zeros, okay, the roots. So I've got this root here. This is at negative 3. This has got a multiplicity of 2. And I've got one here, looks like at 1. And it's going to have a multiplicity of 3. Okay, so right now, I can write this out. Now again, I'll do it on here so I can kind of save space here. My function at this point is going to look like this. Y equals, again, I'm going to have some sort of vertical stretch here that I will determine in a second. Okay, so negative 3, that means my factor is going to be x plus 3. It has a multiplicity of 2, so this is going to be squared. Then I'm going to have x minus 1. And based on the way it's going through, that'll have a multiplicity of 3. Excellent. Now, I also know that it goes through the point, based on my scale here, negative 1, 8 here. So negative 1, 8 is that point right there. So if I plug 8 in for y, I should be plugging negative 1 in for x. All right. Now I just evaluate. Negative 1 plus 3 will be 2. Squared is 4. Okay. Negative 1 minus 1 is negative 2. Cubed is 8. So 4 times, is going to be negative 8. So 4 times negative 8 will be negative 32. And when I divide, I'll get negative 1/4 is equal to that a value, that vertical stretch there. And it's going to have a reflection, obviously, as well. Which actually makes sense, because notice that the graph it's definitely an odd function, and it's dropping as you go to the left. Its end behavior is going to go from quadrant 2 to quadrant 4. That implies a negative leading coefficient there. So that makes sense that it would be negative 1/4 x plus 3 squared times x minus 1 cubed. That's the equation of the graph that we're seeing right there.
The graph below has x-intercepts negative 3/2, 0, and 2, and passes through the point 1, 3. Find the equation of the graph using only integral linear factors.
Okay, so to do this one right here, this question is really no different than the ones that we've just been doing here. What they're doing though is they've listed off the roots right here. So we can see right now that x, for our x-intercepts here, are going to be negative 3/2, x equals 0, x equals 2. And we're supposed to come up with the equation of this polynomial using just integral linear factors, meaning no fractions. This is really what they're trying to get rid of here. So I know that as a factor, this is going to correspond to just x. Actually, I'll even do it. You'll lose a little bit better here. I'll start with this one. In order to get my factor from this, I'm going to multiply by 2 to get rid of the denominator. So 2x equals negative 3. And then I would bring that 3 over. So 2x plus 3 is equal to 0. So now I got this term equal to 0. There's my factor. In this case right here, x equals 0. Well, it's already equal to 0. So that's my factor, the x. In this case, bring the 2 over, equals 0. There's my factor. And so now what I've got here is y equals, there's going to be a stretch factor there somewhere. But my factors here are going to be 2x plus 3, okay, x, and then x minus 2. Okay, those are my factors right there. Notice that the multiplicity of each 0 here is 1. So that's exactly what I was expecting. Okay, Now, I also know that it goes to the point 1, 3. So when y is equal to 3, x is 1. Let's evaluate that, see what we get here. 3 is equal to a times what? Well, 2 times 1 is 2, plus 3 is 5, times 1 is 5. 1 minus 2 is negative 1, times 5 is going to be negative 5. So when I divide, I'm going to get negative 3/5 is equal to a. And that's great, actually, because when I look at this, I'm seeing a cubic, but I'm seeing a negative cubic because its motion is downward. The end behavior is from 2 to 4. That suggests a negative odd here. So perfect, negative 3/5, exactly what I was expecting there. So now I come up here, I'm going to write out my answer. Therefore, the equation will be negative 3/5. Okay, what did I have here? 2x plus 3 times x. I could probably move that x up front. That's probably a better way to write that, but it doesn't really matter. And then x minus 2 at the end there. That's the equation we're looking for.
A polynomial equation has the following three roots. Negative 2 is a root with a multiplicity of 1. 1/3 is a root with a multiplicity of 1. 1 is a root with a multiplicity of 3. The graph of the corresponding function has a y-intercept of 2/3. Determine the equation in factored form.
All right, this question is essentially asking what a lot of the previous ones have been asking here, just doing it without the graph here. We don't have the luxury of having the graph. But we are told a bunch of things here. So I'm going to lay this one out. We know that there's going to be a stretch factor there. There's always a stretch factor. It might just be 1, but still, the a is still there. It says that we've got x minus 2 as a root. So that means the factor, corresponding factor is x plus 2. It's got a multiplicity of 1. Okay? We've got 1/3 as a root. Okay, so now let's think about this. We got 1/3 as a root. X equals 1/3. I need to make this equal to 0, but I need to do it by getting rid of the fractions first. So I'm going to multiply by 3 and then bring the 1 over. Ah, that's the factor I'm looking for. 3x minus 1. Okay, so I come back over here. 3x minus 1. It has a multiplicity of 1. And then 1 is a root. Okay, so that's x minus 1. And it has a multiplicity of 3. There we go. So again, the big trick to this one, again, is remembering that when you've got this fractional root here, I need to undo the division that occurred to get that fraction. I need to multiply to get that back up, okay, into the numerator, and then I can bring that 1 over, and there's my factor. Okay, good. I'm almost done, actually. Now, it says the graph of the corresponding function has a y-intercept of 2/3. Okay, y-intercept of 2/3, that occurs when the x-coordinate is equal to 0. So now the question is just about evaluating this. So 2/3 is going to equal a multiplied by what? Well, 0 plus 2 is 2. 3 times 0 is 0, minus 1 is negative 1. Negative 1 times 2 is negative 2. Negative 1 cubed is going to be negative 1 times negative 2 will be positive 2. Oh, it's when I divide here, I'm just going to get that a is equal to 1/3. Great. Now, putting that all together, my equation will be y equals 1/3, x plus 2, 3x minus 1. These are both to the 1. And then finally, x minus 1 cubed. So there's the polynomial that we're looking for.